variables affecting cohesion that we discussed last time are, first of all, the clay mineral kind. That's really important. You saw the wide range of cation exchange capacities and surface areas and shapes that clay minerals have. And as you can imagine, the cohesion, the strength of the interparticle bond cohesion changes with the shape and surface activity of the material. Also changes with the cation concentration. We talked about that at some length. That is the cation concentration in the ambient water, the general cation. The valence and hydrated size of the cations, remember we said they can't get closer to the surface of the clay mineral particle than their size allows, and that's the hydrated size, the size of the cation with the water shell around it. And ions smaller than potassium are hydrated. Larger than potassium, they aren't. The reason for that is that potassium is about the same size as a water molecule. When it gets bigger, then the hydration shell tends to be more diffuse, more and the temperature and the pH. All of those things are important when you're considering strength of cohesion. We'll be alluding to these things as we go along. Maybe I should list them. Mineral kind. Kind of clay. Cation concentration in the ambient fluid. Valence and hydrated size of the ions. Temperature. And pH. And this involves the surface area, charge density, on the surface, and the shape. You know, I've said several times, I think, the material that we're dealing with is a mixture of clays, so that we can't idealize these too well. We have to deal with them empirically, and I'll discuss that more. I passed out a curve to you, the one that I don't have any left here, I guess. One left? Yeah. This one. And I'd like to describe how it was obtained and use it to illustrate the importance of the relation between cation exchange capacity, sodium absorption ratio, and the kind of clay. These curves were obtained by consolidating a synthetic soil, a soil made of different kinds of clays and finely ground quartz, to make a saturated, consolidated soil, so that the structure was always the same. The way the particles were put together was always as similar as we could make them. Then that cylinder, it was made in a cylindrical form, was placed inside of a lucite outer cylinder. The cylinder of the soil was placed inside of a lucite outer cylinder, and this space was filled with water. Then the outer cylinder was rotated at various speeds, and see, the water was up like this. It's actually a metal plate here and a metal plate here, so only the side of the soil was exposed. The outer cylinder was rotated so as to produce a fluid shear stress on the surface of the soil, and that shear stress could be measured by a torsional device on the support for the cylinder of soil. And by rotating this at different RPM, we could get different shear stress on the surface of the soil. And if you plot and we'd run it for, say, 1 minute, rotate it for 1 minute, then take the sample out and weigh it, and then put it back in and rotate it for another minute and take it out and weigh it. And if you do that, then you find time and weight loss to look like as it'd be linear, or this is 0. Then if we did it at another RPM, this is shear stress 1, we'll say, we'd get a similar plot that looked like this, and another shear stress, and so on. So at different shear stresses, we could measure the rate of erosion rate, or the weight loss. Then taking the slopes of those, which is the erosion rate, I'll call that E dot. We could plot shear stress against erosion rate, which is what we're really interested in. And we have these we could plot these, and what we would find is that they would plot something like this. So we could, this is a straight line because the material that we're eroding is uniform with depth. That is, doesn't change with depth. So that we could find a critical shear stress below which erosion rate was 0. And that's a measure of the strength of cohesion. Do you follow me? In other words, it takes so much shear stress to initiate erosion. This plot is a plot showing critical shear stress, this value here, measured under different conditions with different amounts of clay and different kinds of clay. And the two conditions are the sodium absorption ratio. On the bottom it's 48, and on the top it's 2, which means that on the top there's a lot of multivalent or calcium and magnesium ions relative to the sodium ions, and on the bottom there's a lot of sodium relative to the magnesium. And you can see that with increasing cation exchange capacity, more clay in the soil, for any of the clays, that these followed a consistent curve, which means that cation exchange capacity is a useful measure of the surface activity of the clay, its ability to bond, and that the more cation exchange capacity, the stronger it is when the particles are really cohesive. So it's an illustration of the bond strength, or the cohesion, that we've been talking about. Now, it's not material in suspension. It's material, in this case it's soil, but it's a way of measuring the strength of the cohesion. As we pointed out last time, it takes very low concentrations of sea salts to make clay particles cohesive. Remember, we said about one part per thousand for kaolinite and about 2+ parts per thousand for montmorillonite, which is not very high compared to the 33 or 34 parts per thousand of seawater salinity. The importance of that observation is that practically that the suspended clay minerals in an estuary, over practically the entire estuary, from way upstream where the water, river water mixes with the ocean water, are cohesive. So normally we don't worry too much about whether the particles are cohesive or not cohesive, except right up in that upper zone. Do you follow me? It removes a big problem for us. if we had to account for changes in salinity throughout an estuary in computing sediment transport, that would really add a complication to our problem. But we can say that when the concentration is more than a few parts per thousand, that all the particles are cohesive. Now there is some increase in strength at the lower concentrations. Particle strength, interparticle bond strength increases up to about, well, at most 10 parts per thousand. But still, it's cohesive enough so that you can regard the particles as cohesive well up into an estuary. I'll come back to that point. And it turns out that particles that deposit down an estuary ways may come back up the estuary along the bottom because of hydraulic conditions there, and they bring with them some of their salts and their cohesion. So the process right at that boundary, the river saltwater boundary or region, is a little diffuse. It's a little unclear. But other than that, you can just regard the particles throughout an estuary as being cohesive. That's not the case in rivers, however. If you're dealing with a river that flows through limestone formation, then you may have variations in the cohesion of the particles. But in estuaries, it's not. And I should say something about other forms of cohesion. We've talked at length about clays because that's the big problem. But or some kinds of organic matter are cohesive. Bacteria exude a polyuranase or polysaccharide material from their surfaces that under some conditions makes them cohesive. That is, they just stick to each other. Algae, when they're young and growing and multiplying, tend to have negative surface charges and repel each other, tend to stay apart from each other. That's a healthy thing for them. You know, they want to be exposed to light and nutrients. But when they get old and senescent, then they become cohesive. And in fact, they form objectionable mats on the surfaces of eutrophic lakes, you know, that blow up on shore and decompose and smell. But the important thing is that the interparticle cohesion of algae is commonly negative. That is, there's repulsive when the algae are young, and only when they get old and tired do they get cohesive. There are other factors that are brought out in some peculiar circumstances. For example, if you have a filamentous mold in suspension and bacteria, you can have the entanglement processes. I think you see that in activated sludge clarifiers, for example. I think those are the main factors affecting cohesion. Oh, I should know one other that's important, that at least is brought up often. I don't know how important it is. Filter feeding organisms like clams and mussels that obtain their food by pumping water through filters, internal filters, accumulate particles and bond them in a kind of a zoogleo mass and expel them in a kind of a pseudo-feces. And these leave pellets around on the surface of the mud, or maybe under the mud in the case of clam. And this bonding is believed to make bottom mud more resistant to erosion than it would otherwise be. I've not had good examples of that. It's been described by biologists many, many times, but I've not yet seen real good examples of places where that is important. But I want to mention it to you because it may be under some circumstances. Then I guess before leaving the subject, I should say that there are substances, commercial substances that you can buy that make particles cohesive. Polyelectrolytes that are sold by Dow and other companies for water treatment processes, for example. Interesting side story about Dow and their polyelectrolytes. When they first came out in the 50s, 60s, about the early 60s or mid-60s, they believed that they were going to solve all kinds of problems. And one of the problems they were going to solve was reducing the dredging problems and clarifying natural waters. And they set up an experiment in Montezuma Slough down here in San Francisco Bay, where they had a pipe across the slough and they fed a polyelectrolyte, Separan was the one that they used at that time, polyelectrolyte into the water. And they had talked to me about it before that, and I said, well, the particles are already cohesive. You know, you're not going to make much progress by just adding more, making them more cohesive, unless you bring them together somehow. And they said, well, you know, when we shake them up in a graduated cylinder with this, they settle out faster, so we're convinced it's going to work. And it was a fairly expensive field experiment. They spent 24 hours out there pumping this stuff into the water, and there was no change in concentration of suspended solids upstream or downstream. You know, the whole day showed zero results. Particles were already cohesive. If they were going to combine, they would have. But polyelectrolytes are important in lots of commercial processes, you know, in water clarification. Okay, that's all I want to say about cohesion for now. What we'll talk about to the rest of today is aggregation processes. In order for aggregates to form, the particles first have to be cohesive, and second, they have to be brought together somehow. Remember, the forces that make the particles cohesive are very, very short range. In fact, you can regard them as so short that the particles have to collide. You know, on the scale of the particle size, the particles have to be brought together somehow. And there are three processes that bring particles together. The first is Brownian motion. The second is velocity gradient. And the third is differential settling velocities, or I'll say different settling velocities. The first one I want to talk about is Brownian motion. Recall I described ions in solution as being constantly moving because of thermal motions of the water. Well, those thermal motions of the water affect particles even as large as clay and silt mineral particles. The reason that they're called Brownian, that this process that I'm describing, jiggling of particles by the thermal motions of the water molecules, called Brownian motion, is because a man Brown first looked through a microscope and looked at a drop of water with particles in it, and saw these suspended particles constantly jiggling. And if you wish, you can take one of our microscopes and put a drop of water on a slide with particles in it and look at them, and you'll see that you can't make them stay still. They're constantly jiggling. It's just the thermal motions of the water molecules striking the surface of the suspended particles. And of course, they're striking them all around. But because the motions are distributed, that is, some are more than others, and because they hit the particle in different directions, the particles tend to have a rotary motion. So if you have a particle something like this, the water molecules are striking it everywhere, some much harder than others. But the sum of them is never through the center of gravity. So the result is the particle is always rotating. That is, it rotates this way, and then it rotates that way, and then it rotates this way. You follow me? And in the process, it's moving side to side. If you have a few minutes sometimes, look at some suspended particles under a microscope and watch that. Well, this constant motion and jiggling, when there causes the particles, of course they're being translated in one direction and another, and so on, causes particles to collide with each other. If they're close enough together, that is, they'll collide, or if they're far apart, it may take a long time, but they'll eventually cross paths and make them collide with each other. And if they're cohesive, they'll stick. When they collide, they'll stick. In order to get some insight into this process, that is in terms of rate and importance, the rate that it occurs and importance of it, I'm going to go through some mathematical descriptions. Now these and the subsequent mathematical descriptions are greatly simplified descriptions, and they're presented just to give you insight. I don't want you to memorize derivations or anything like that. I want you to understand processes so that you can recognize when they're important and when they aren't. And I'll just give you the classical description. Let's first of all, regard the particles as spherical. That's a great simplification. But the fact that they're rotating continuously makes them occupy a volume that's something like spherical. So I'll draw now spheres, and for now I'm going to make all the particles the same size. We'll talk about different sizes later. And we'll call the radius of the sphere r sub s, and the distance between spheres, or I should say the distance between centers of the spheres, we'll call r. Okay? And if we slide into our habit of continuum descriptions, we can say right off that r, the number, and we'll talk about the number of particles, n is number of particles per cubic centimeter, or unit volume. I'll use cubic centimeters. And we can say that n at r sub s is equal to 0. That is, the closest a particle can be is 2r, right? We're talking about distance between the center. So we'll say the number at rs is equal to 0, and the number at r equals infinity is equal to n0. That is the ambient, the average concentration throughout the system. And then I'll present without further explanation, unless you really want it. We can write del squared n at r, equals 0. Are you all familiar with this notation? Partial derivative of n, second partial derivative of n with respect to r. In this case, we're dealing with it in one dimension, is equal to 0. Does that help? A little bit. And so we have two conditions and a relationship that we can solve. I might give you a reference. Smoluchowski, at least I'll give you the names of the people, came out with this in the last century. Since then, it's been improved by Whitlaw Gray, and Patterson. These are the names you'll read in the literature. Anyway, the solution to this set of equations is 1 over n minus 1 over n0. No, I'm sorry, I'm 2 steps ahead. We can write n at r is equal to r sub s n0 times 1 over r sub s minus 1 over r. And you can satisfy yourself if you want by going back on that. And I'll call this this equation 1, and this we'll call 2. So this gives us a distribution of particles around an individual particle. Okay, we're looking at one particle. It's a distribution by concentration and number concentration of particles all around this one particle. Now we can describe the flow of particles toward the individual particle by describing the flux of particles through a sphere. Let's consider this is the central particle we're concerned with, and we'll consider a sphere around that particle. And the flux of particles through this sphere toward the central particle. And I'll call the flux J. And it's due to thermal motion, so we can say it's diffusion. The total flux toward it has to include the surface of the sphere, which is 4 pi r squared, times the diffusion coefficient, d times the concentration gradient, which is dn at r, divided by dr. So this is the area of the sphere. Surface, diffusion coefficient, and this is the concentration gradient. For those who are interested, this is called Fisk's law, Fisk's law, isn't it? Well, I better not say it if I'm not sure. Anybody know? Fisk's? Fisk's law, that's it. That is, that particles migrate down a concentration gradient. And the rate of migration is proportional to the concentration gradient. We'll call this 3. Now at r equals 2 rs, that is when the particles just touch this one, 2 times the radius of the particles are removed from suspension. That is the number of particles. If we call now the combined particles as one particle, we can say the rate of removal of the number of particles per cubic centimeter is the rate that they approach 2 rs. So if we combine 2 and 3, we have
Why are they necessarily removed?
removed?
Yeah.
Well, we're saying that the particles are cohesive. Okay? And when they collide, that they stick to each other. Now we can modify that by giving it a sticking coefficient. We can say some fraction of them stick, and I'll do that later. I'm trying to keep it as simple as I can.
Are you saying then that they're unavailable for further interactions with other particles?
When the particles are all moving due to the thermal motion, okay, and they're moving toward one of the particles. We're looking at just one particle towards which the others are moving. And we'll do this say this for all the particles later. But right now we're concerned with a particle and the flux of particles moving toward it. And the statement I just made is that when they collide and stick, that makes two particles, now one particle. It's a one aggregate. We'll call an aggregate a particle. So if I combine these, I can write J now is equal to 8 pi r sub s times d n0. I combine 2 and 3 and substitute rs equal r. Okay, so what we're really concerned with now is all the particles, that is every particle. And we can say that every particle is removing other particles the same way, that each one acts as a collecting sphere, so that now we have n times this process going on, right? And we can write then dn dt equals minus, because it's decreasing, 4 pi r sub s divided by, times dn. That is the rate of decrease in numbers of particles. That should be average concentration. I'll call it, we've been calling it N0. I'm going to call it average concentration squared. So this is for all particles. This is, maybe I'd better, before I leave this, this is the rate of decrease in numbers of particles. This is, we'll call it effective diffusion rate coefficient. And this is average concentration. If we assume, now that's the case for spheres all having the same size. If we assume that the spheres have different sizes, then we have different diffusion coefficients and different sizes. Let's take a look at two sizes, just two size. Add one complication to it. And for that we can write minus dn dt is equal to 2 pi r1 plus r2 d1 plus d2 times n bar squared. Still greatly simplified. Only two particle collisions and two different sizes. I'm going to define this R1 plus R2, which might look something like this, for example, a large one and a small one. The sum of the radii we'll call this the ith particle, and this the jth particle. So this we'll call this capital R I J, and this is referred to as the collision radius. So we have minus dn dt is equal to 2 pi capital R ij B effective times n squared. Important thing to recognize is that the rate of loss depends on the combination of the sum of the radii of the colliding particles and the concentration squared. So changing the concentration has a big effect on the rate of collision, as you might have gathered intuitively just looking at the problem. With this, the Rij and N combination leads to some curious situations. One is that if you have a few large particles and many, many small ones, which is not an uncommon situation, it appears that gives you a combination of a large, for collisions between the small and the large particles, large Ij and a large N. So it appears from outside the suspension that the big particles go around scavenging up the little ones. The big ones get bigger, kind of thing.
I have a question.
Mm-hmm.
I'm back over here on this equation of the NDT, and I'm not seeing how you derive that. I presume that you're taking the flux and multiplying it by the surface area somehow, and from that getting the...
Not somehow. A flux is a rate of particles per unit area, right? And so to get the total flux toward the particle, you have to include the area of the sphere, of the surface through which they're migrating, right? And the area around the spheres is what took as a spherical area as 4 pi r squared. R gets lost in here somewhere in the algebra. We substituted r sub s for r. Let's see, we combine 2 and 3. Oh, it gets lost up here when you combine these two. And set R's. You can sit down and work it out.
You're saying it's basically straightforward.
Yeah. Yeah, this is average collisions per second, if you like. Average of the collisions per second.
This what was bothering me was the n squared term.
Here? Oh, the rationale for that is that this is the collisions on an individual sphere, okay? And for every sphere, if you say the collisions on every sphere are the same as this, then you have to multiply that by n to get the total collisions in the suspension. So that makes that n squared.
If you're looking at removal, don't you double count? These two will come together. You didn't remove both of them.
Didn't I change from 2 to 8 to 4? Yeah.
But you aren't removing both though, are you? You're just making 2 into 1, so you really only remove...
Yeah.
So,
It's here. You know, I'm sorry, it's a little bit confusing, 'cause it's sort of sleight of hand. This is a really idealized description, but it brings out the important points. The fact that it goes up with the square of the number of, that is the rate of removal goes up with the square of the number of particles, and that the frequent rate of removal also depends on the sum of the radii of the colliding particles. Well, we have a ways to go yet. We still don't have a description of D. So let's work on that. We can say that Albert Einstein you'll see lots of famous names associated with particle dynamics because it's a challenging problem, and people have been fascinated by it over the years. He said that for diffusion of gases that D is equal to KTB, where this is the average thermal energy of the suspension. And this is the energy dissipation, or 1 over the drag. And Stokes, in Stokes' law, said that the drag is equal to 6 pi for spheres, eta r, where eta is the viscosity. And the unit is poise, or dyne seconds per square centimeter. There are other units too, but that'll do it for now. So this is the drag, and it essentially assumes that the particles, that the suspended particles can regard the fluid as a continuum, or in other words, that the particles making up the fluid, the water molecules, are very, very much smaller than the particles diffusing through it. So we can write then that the diffusion coefficient is equal to kT divided by 6 pi eta r. So if we combine now I've stopped my numbering system. We combine this with that relationship. We have minus dN dt is equal to 2 kT divided by 3 eta times R1 plus R2 divided by quantity squared divided by R1 times R2 times n bar squared. This is, if the particles are the same size, R1 plus R2 is 2R squared, is 2R, and square that, that's 4R squared. 4R squared, and this is R squared. Oh, I left something out here, 4. Okay, and this is R squared, 4R squared, so that when the particles are the same size, this is just 1, right? And we can put in here, to accommodate your question about the particles being removed, a sticking factor, which I'll call S here. So that we can say that if the sticking factor is 1, every collision results in a cohesion, then that's the rate of removal. If it's something less than 1, then the rate of removal is somewhat slower than that term. And this accounts for the fact that when that smaller particles have larger mobility than large particles. That is, the bombardment by the water molecule moves them more than otherwise. Well, now with that under our belts, let's look at it from a more practical standpoint. Let's consider uniform particles for now, and we can rearrange our relationship over there. 1 over n dN dt. I'll put the minus on this side, is equal to 2k T s over 3 eta times n. This has the dimensions of 1 over t, and and I'll make this average, and this we'll call a average time between collisions. Okay, so I'll put this t sub c, the collision time, and the time between collisions is directly proportional to n, goes up with t. Viscosity of water changes very rapidly with temperature, however, so when you use this relationship, it's necessary to take into account the fact that viscosity of water is a function of temperature. I'll put T, if you like, there. To give you some idea, the viscosity of water at boiling is 1/6, roughly, of the viscosity of water at melting. Changes by 6-fold from melting to boiling. Temperature has a big effect on its viscosity. So we can call this 1 over Tc, or we've been calling this J earlier. J is the collisions per second. This is 1 over J, collisions per second. Oh, is that right? Yeah, collisions per second. Yeah, no, this is J, what we call J. And call time of collisions or time of coagulation in various parts of literature. We can represent this relationship, integrate this relationship for the simplifying conditions that we had, and find the commonly expressed minus 1 over n0. 8 pi r sub s d times t. I'm sure you've all seen this before.
Two questions. I don't understand the reciprocal of a time unit is a flux. Is that what you're saying?
Oh, this J was I used J for two things, didn't I? Yeah, I used it for two things. No, it's not the flux. We'll just leave it, and I'll not redefine J. Just 1 over T. This is 1 over the time of collision time.
And where is that used? Does it appear something 1 over time of collision?
Where is it used?
Yeah, is it someplace, is it above and then?
Well,
My second question, I guess you have a 3 eta something, and I
yeah,
can't.
this term here is 1 over the collision time. Okay?
Okay. I've got one more question. On the right-hand side, right above your right hand there, what is that?
That's viscosity.
You know, the thing to the right of it, yeah.
I just put that in there to show that viscosity is a function of temperature. Maybe if that's confusing, I'll take it out. But I do want to emphasize that point. Viscosity is very sensitive to temperature. Well, I'll not spend a lot of time at it, but we can put this back into its definition and wind up with and rearrange this algebraically to find that n at any time t is equal to n0, how did I put it, divided by 1 plus t over t sub c. And this relationship looks like this. T in this direction, n in this direction, and with, let's say, this is n0. It has a shape something like this. So at 1 t sub c, about here, The value is at T, this is 1, so it's 1/2 N0. At 2 T sub C, it's 1/3 N0, and so on. So it falls off in a roughly hyperbolic way. The important cases are when T is very much larger than T sub C, or T compares with T sub C. If it's very much larger, then this changes very slowly out here. If it compares in size with T sub C, then the number changes rapidly. You follow me? So we'll be, off and on, we'll be talking about T being very much larger than T sub C, or T being comparing in size with T sub C. I see some puzzled looks.
I'm not sure what T sub C is.
T sub C is the average time between collisions of particles.
T is the time you're interested in?
T is the time after some point. You know, you have a starting point where there's so many particles in suspension. Let's say we start out with dispersed suspension, and we add to it some aluminum ions, and then we let it stand there. Somehow we magically get that aluminum all through it, and we let it stand there, and the particles collide with each other, and then the time of collision, the initial time of collision. Yeah, this is at the starting time, the time of collision at this point, and then we look at that multiples of that time of collision. Everybody clear?
So as you remove particles, your time just increases. Is that what this is showing?
This is the number of particles,
And the number goes down, and the collision frequency decreases.
and the frequency decreases because there are fewer and fewer suspended particles.
Have you had, precisely maybe, when you've gone through the derivation, have you included the aggregation, the size of the particle? So that drops out, doesn't it?
Yeah.
The size of the particle doesn't factor.
The size disappeared out of that when we got into the diffusion, included it in the diffusion coefficient from this.
Okay, I see it.
Andy? All clear?
Okay, I got confused. You used J for flux, and then you used J for something else. And the equation where J equals 8 pi R sub S D N sub naught, what does J stand for?
Oh, cross that out. It's in my notes that way, and I put it on. I used to describe this as J for Brownian motion, H for Hij, I for velocity gradient, and K or H for differential settling. But that's confusing, so please, if you copied that down, cross it out and call it 1 over T. Any other question?
I think she's referring to the flux term.
What's that?
I think for J she just
Yeah, J was I used it for the flux earlier, and let's just leave it at that.
RSD and not is still accurate. That's a problem expression. That's not the one you want to do.
J is the flux toward the individual particle. I'm sorry about that. A couple more things I'd like to say about Brownian motion coagulation. First of all, we can use this relationship to calculate the 1 over T sub C. And for let's say for 5 degrees centigrade and for 20 degrees centigrade, common range of temperatures in estuaries, we find that 1 over T sub C is equal to 5.4 at 5 degrees centigrade and 3.4 at 20 degrees centigrade times 10 to the minus 12th N0, or N bar, I've been calling it, per second. In other words, it takes, in order to have one collision, or let's say 5 collisions per second at 5 degrees centigrade, it's necessary to have 10 to the 12th particles per cubic centimeter. So you can see that it's only important at high concentrations. 10 to the 12th particles per cubic centimeter is a lot of particles. And it turns out that for average estuarial sediments, that's on the order of 10 grams of suspended solids per liter. So, and I'll bring you a sample of that next hour so you can see what that looks like.
Were you saying that's the number you need for collisions or for the TCT in 1 second?
It takes 10 to the, well, the time of collision, the collisions per second are 5 times 10 to the minus 12th times the number of particles per second. So if you want to get 5 collisions per second, you have to have 10 to the 12th particles per cubic centimeter. 10 to the 12th. That's a large number. Which means that the concentration has to be really high. And that, for ordinary muds, is about 10 grams per liter.
With 5 particles a second, is that what you said?
Yeah. Or 1 collision per second, you have to have 0.2 times 10 to the 12th. That's the first thing to notice. It's only really important at high concentrations. The second thing about it is that the particles come together in a random motion. Remember, I described the particles as having rotary motion in the suspension, and they collide in all kinds of random ways. And the resultant aggregate is a very loose, lacy, weak aggregate. It's easily torn apart again. It's in fact, sometimes they appear to be stringy. That is, there'll be particles in strings with big gaps, big holes in it. And these particles tend to be, these aggregates rather, tend to be very weak and easily torn apart. So it produces aggregates having low density and little strength. I'll call it rho sub A for aggregates, low shear strength. And before I go on, I should point out that these two, when this one is present, then you have both of these. And, well, better way to say it is Brownian motion goes on all the time. You know, there's no way to stop it. But it only becomes important when the concentration is high enough so that its rate of aggregation is appreciable. Okay, now for the next few minutes, I'd like to talk about velocity gradient aggregation. This isn't nearly as complicated as Brownian motion. Let's consider, I'll make a large particle like this, spherical particle again, and we'll consider aggregation in a velocity gradient. Maybe before I go on, I should describe that for you. Consider velocity u with distance, let's say from the bed. I'll call it z, distance from the bed. So we have a velocity gradient that looks something like this, let's say. A velocity profile that looks something like this. So here we have a gradient in velocity in the z direction. You all follow me? if we have a particle suspended out here, some kind, and another particle displaced from it in the velocity gradient, this particle will have a velocity of, say, that, and this one will have a slightly greater velocity. Furthermore, the velocity on this side of the particle will be less than the velocity on this side, so the particles will rotate. Here, I'll get the picture. Now, as these particles are moving along, rotating like this, one gradually catches up with the other one, and if the distance between their centers is less than the radii, less than Rij, then the particles will collide. That is, they'll eventually come together and collide. Now, keep in mind this picture of the particles rotating, and then they collide. And when they collide, there's some shear stress between them because they're both rotating. What we want to do first is to calculate the frequency of collision of these particles, just like we did before, so we can calculate the rate of removal. And I'll assume that the flow is in this direction, just for convenience, and that there's another particle that collides with it. When it collides, the sum of the radii, this is Rij, so that we have now a sphere like that, a collision radius of Rij. Let's say the velocity is in this direction, and that the velocity gradient, the particles all moving with the fluid, but now we're really concerned with just the gradient to determine their frequency of collision. And I can show this gradient as a linear one for first approximation. That is, so the particle now sees it's all moving, but the gradient makes the relative motion across the center of it, of the particles, such that it's rotating now in this direction. And we can make sure I keep my symbol straight. I'll make this just a general coordinate, Z. And this we'll call the velocity in this direction as U. And let's consider a slice of this sphere hard to make a three-dimensional picture on a two-dimensional board, but what I'm trying to show you is a sphere like this and a slice through it, and the edge of that slice is where the collision is going to occur, and we want to calculate the collisions on the edge of that slice and then sum up all the slices, okay, so to get the total collisions on the particles. And I can write now, and notice, one other assumption I'm going to make is we'll neglect the curvature of the streamlines around the particle. That is, we'll just consider the particles as coming directly toward it. Okay. So we assume spherical particles, and we're neglecting curvature of streamline. From this, we can say that the U. See, I better simplify my description here. Let's call this U here. That way I don't have to go through another derivative. So U is equal to Z du dz. And Z I'll draw a line up here help us, and we'll call this angle theta. Okay. And Z is equal to Rij sine theta. And because I'll need it later, call this 1, 2, and 3. I'll take the derivative of this, dz is equal to Rij cosine theta d theta. Combining 1 and 2, I have u is equal to Rij sine theta du dz. Okay, so the number of particles now that pass between z and z plus dz, that is, it hits this slice now, and that will collide with a sphere each second, are d. I'm going to have to revert to my I. I is the collisions per second. And we can write di then, the part that collide with that slice, is equal to the number of particles per cubic centimeter times the velocity that strike that times 2 Rij cosine theta, which is the area of the edge of the slice. Times dz. And I have this I'll call 1a, and combining, and this one we'll call 3. Combining 1a and 3, we can write di equals 2n du dz times Rij cubed cosine squared theta sine theta d theta. And integrating those, we have I is equal to the integral of di, which is equal to the integral from theta equals 0 to pi over 2, which is equal to, I'll just give you the answer, 4/3 Rij cubed n, well, leave that off, du dz times n. This is now collisions per second. Collisions per second on an individual particle, just like as we did before. Okay. So we can write 1 over t, this is 1 over t sub c is equal to that, or minus dn dt is equal to that squared, just as we did in the past. So this is 1 over n dn dt. the rate of loss of particles. We can, let me say a few things about this in the last few minutes. Notice that the collision radius is all geometry. We just manipulated the geometry of the system. But it shows that the collision radius has a major effect on the frequency of collisions and velocity gradients. It goes up with the cube of the collision radius. So you can see that a large particle has a great advantage over small particles, and it can collect them. Now there's some question about that because we assumed that the streamlines were not curved. And for very small particles, or I'm sorry, very large particles, the streamlines may very well be curved. So the large particles may not have as much of an advantage as it would appear from this. Second thing is that this again depends on the concentration of particles. The more particles there are, the more frequent the collision on an individual particle. And then third, it depends on the velocity gradient. If the velocity gradient increases, then the frequency of collision increases. But remember the picture that I showed you earlier. That the particles are rotating. So that when they collide, the higher the velocity gradient, the more shear stress there is on the two particles, between the particles when they collide. So when the velocity gradient reaches some maximum value, or some value, then the particles won't stick. That is, they may stick instantaneously and then be torn apart again. If the particles stick, then the aggregate rotates thereafter. But if they collide and the stress is sufficient to tear them apart, then they'll continue as individual aggregates, although part of this aggregate may now be on that one, or vice versa. You know, they may tear at a different place. If the velocity gradient becomes still higher, there'll become a point where the abrasion actually begins to tear them up, and you get breakup. So we have a simple relationship, but now we're stuck with the phenomenon associated with the du/dz. High velocity gradients can cause them to break up. So here we can describe, whereas before in Brownian motion we just described collisions and sticking or not sticking. In this case we can describe collisions as causing sticking at low velocity gradients, not sticking at higher velocity gradients, and at still higher velocity gradients tearing up aggregates that could have occurred. This breakup process is really important in open channel flow because we have a vast region, most of the depth, that has low velocity gradients in it. You know, most of the energy is dissipated right at the bed. And then right near the bed we have not only high velocity gradient in the turbulent region, but we'll have some thin layer of viscous flow, I'll describe in more detail later, where the velocity gradients are very high. So particles settling to the bed particles that are settling down have to penetrate this region of high velocity gradients. And if the velocity gradient is too high and the concentration of particles is sufficient so that you have frequent collisions, of course, then you can have them torn up again. That adds a complication to our description. As I'll show you next time, this mechanism is the one that dominates in estuarial sediment transport. And this one's important under conditions where you have extremely high velocity gradients. And this one's important at times near slack water, but we'll discuss that later. I've gone a minute past our time. Any questions before we break up?
Did you want to finish that equation? Started an equation 1 over n down.
Oh, dNdt, that's I.
Oh.
4/3 Rij cubed du/dz times n. This is for the general solution, for the whole rate of removal.
In terms of your model here, I'm not clear why you're integrating from theta 0 to pi over 2, which is kind of how you have it represented. I don't
Where's the problem?
The limits of your integration of theta go from zero,
Over here?
integration, on the integral variable.
Theta equals 0
0 to pi over 2.
to pi over 2?
Explain that a little bit.
Oh, that's, I use theta as the variable because it's just for convenience. But what we did was to go, this is pi, right? So we did it for pi over 2 for our particles sitting in this direction. Particles are coming in this direction and hitting on this slice. And what we did was to consider the slice all the way across. There's a 2 that gets in here somewhere to get both sides of this.
Okay, so you are.
Yeah, we're looking at particles hitting from this side. Particles hitting actually from this side. They're not hitting this side. So they're just hitting from here over on the bottom.
On the left-hand side, you get particles hitting from the other direction.
Well, remember the whole thing's moving together and we're just looking at the gradient in this one direction. So the particles, this particle only sees particles coming from this direction. Now, this particle sees particles coming from this direction. But what we calculated here, at this stage, collisions on one particle, just as we did before. And then to generalize that, we have to have the n squared.
Why is it you don't consider the collisions on this side?
We're calculating particles colliding on this particle, on one particle. So the particles aren't colliding from this side over here. They're colliding here and hitting this slice. So we integrate the slice all the way for this collision
Why aren't
square.
they colliding on the left side?
Why aren't they hitting on this side? Because the relative velocity on this side is negative. Particles hit it from this side up here.
Oh, they're coming from the top.
So, but you're not considering the ones that come from the top.
I think our problem has to do with whether we put a 2 in here or not. Is that right? Is that the question you're asking? What about particles hitting this side?
That's what I was asking.
Now I'm going to have to go home and go through that step by step and make sure that the 2 is in there. I'm sure this is right. I know this is right, but I may have not have described something in the...
In the previous discussion of Brownian motion, you had to divide by 2 so you didn't double count. I think here you
Yeah.
don't have to.
Oh yeah, you have that. That's it. That's the answer. Thanks, John. That's it. Any other questions? I don't want you to memorize these derivations. That's not important. Important is understanding. You know, I can give you much more elaborate derivations. What I want you to understand is the mechanisms involved and the relative importance of the terms. Okay, I'll see you all on Tuesday.
This side, this one, is the same as already.